So we're now going to have a look at what it is we're actually going to be putting inside the diffractometer to do experiments on, and that is the specimen, the portion of sample that you want to study. In this talk, I'm going to talk specifically about our Bragg-Brentano machines, like the Siemens D5000 and the D2, but some of what I say will also be applicable to the transmission mode study machines. Specimen preparation is really, really important in X-ray analysis, and it's something that a lot of people overlook. This quote from Picharsky and Zavalny I find particularly potent, and it really is hard to overemphasize how important sample preparation is, because it is always under the control of the person doing the experiment. Poorly prepared samples will give you bad data, there's no question about that. It's really a case of the old saying, garbage in, garbage out. And if you don't pay attention to your sample preparation, it's very likely that you'll be coming back to redo your X-ray analysis at a later time. So what would an ideal specimen look like? Well, it would contain an infinite number of individual particles in an infinite number of orientations within the irradiated volume. And that's not something that's really achievable, but we need to get as close as we can. So, as we go through this, I'm going to be talking about our standard Brooker sample holders, which have an aperture in the middle there of about 25mm diameter and 1mm depth. And these are very typical for all of our Bragg-Brentano machines. One of the ways we can increase the number of particles within that volume is to reduce the particle size. You can see at the bottom here a graph showing what the optimal packing density would give us. So for a 100 micron average particle diameter sample, we would fit within that holder about 1 × 10⁶ particles. By reducing the particle diameter, you can see that we exponentially increase the number of particles within the sample holder. And in fact, if we can get it down to 1 micron, then we have 1 × 10⁻11 particles within the holder, which is many orders of magnitude more. Why is this important? Well, it's summarized well in this book, Structured Determination from Powder Diffraction Data by David et al., which showed that good sample processing was really key. And what they've done is to summarize some of the computational and experimental work that's been done in this field to study the effects. And what they showed was, it's summarized in this table here, if we have a 40 micron average crystallite diameter in our sample, within a 20 cubic millimeter volume, we would have about 6 × 10⁵ crystallites. The number of these that would actually be meeting the Bragg condition at any given angle could be as low as 12. And that means we would only have 12 crystallites contributing to our diffraction. Clearly, this is going to give us bad intensities and unreliable counting statistics. Experiments are going to take longer than they might otherwise do. Reduce the crystallite diameter to 10 microns, we get more crystallites in our sample holder, and 760 of these would now be contributing towards the diffraction. Get the crystallite diameter down to 1 micron, however, and we now have nearly 4 × 10⁻10 crystallites within our holder, of which 38,000 should be contributing towards the diffraction process. This is going to give us much better data, better intensities, and more reliable, more reproducible intensities. Orientation was another factor that we mentioned. For XRD, you want a completely random distribution of orientations of crystallites within the specimen, and that may not always be possible. In fact, for most specimens, you'll probably have at least some degree of non-randomness in the distribution. This is going to be particularly problematic, however, when the sample contains anisotropically shaped particles, for example, platelet-shaped or needle-shaped particles. Particularly if you think of how we prepare samples for Bragg-Brentano geometry, we tend to put them into a sample holder, press down, and smear in one direction. This is going to introduce non-random particle orientation, what we call preferred orientation. This can cause huge changes to the intensity of the Bragg reflections. We can see an example of this here in these two plots. In plot A, we have a nice, well-ground powder that is coming from a material that's obviously been well prepared, and we can see that we have the full full range of Miller indices. So we have different 00L type reflections, plus we have, for example, 115, 111, 119, and so on. We see all the reflections we should do. However, in the second case, B, this sample has not been ground and it's not been well prepared, and now, even though the sample is exactly the same chemistry, same material, just not well ground, we're only seeing the 00L type reflections, and all of the other information is being lost. You can imagine very easily that this will be very confusing to try and analyse at a later date. One thing I should also mention here when we talk about preferred orientation is some people will tell you that rotating the sample during the experiment will improve the preferred orientation, and this is not true. A sample that is has bad preferred orientation at 0 degrees will still have bad preferred orientation if you rotate it around to 90 degrees and so on. What sample rotation will do is increase the chances of particles meeting the Bragg condition, so it will give you a small boost to the intensities. But hopefully this shows you the proper sample preparation really is the key in trying to minimise preferred orientation. If your sample is non-ideal, you can still collect meaningful X-ray data, but just bear in mind, the further your sample deviates from optimal, the worse the data are going to be, so the longer you might need to run on the machine. Clearly, if you can't fill the holder, that's going to have a big impact on the data quality. And if you're looking at very small samples, powder samples, then you probably want to be using transmission mode, which we have the Stowe machines which look at milligram quantities of powder. If you have very small sections of, for example, a tubular section of metal that's been sectioned, try and include as many of the sections as possible rather than just looking at one. And also, it's worth mentioning here, consider running them by Scherrer geometry if you've got powders where preferred orientation is a real problem. Because running in a capillary in by Scherrer geometry is an option for us. We do have machines capable of that, and it is the best way of getting around to preferred orientation. Finally, once you've made the sample and you've got it in the holder, it's worth reiterating the comments from previous videos about specimen height displacement. That is, make sure the sample is at the right height in the machine, and it should be level with the top of the holder. Whatever holder you're using in reflection geometry or Bragg-Brentano geometry, make sure that the sample is level with the surface of it. This is the most common error we see in the lab by far. People put in samples at the wrong height. If the sample is at the wrong height, you will unquestionably see a shift in the peak positions, which can make your analysis a lot harder very quickly. And the height only has to be off by fractions of a millimetre for a noticeable effect to occur. So hopefully this talk has given you a good impression of some of the key factors that you need to consider when you come to prepare specimens for X-ray diffraction analysis.